So what is an earthquake? The textbook definition is a sudden release of energy. Usually this happens along faults, but it can also happen around volcanoes. Don't worry about mineral transformation earthquakes. It's a pretty obscure topic that we won't be covering in this class. The elastic rebound theory is the prevailing understanding of how an earthquake happens. Imagine that strain is accumulating on this fault, but an earthquake hasn't happened yet. As strain accumulates, there's a little bit of flexure, but no snap. More strain accumulates, but friction prevents the earth from snapping. Finally, the pressure is so strong it overcomes friction, and boom, we had an earthquake. The survey line could have been a fence, it could have been a highway. Any example of something crossing a fault has been ruptured. This energy travels in the form of seismic waves. The earthquake happens beneath the Earth's surface at a focus. But since we don't live below the Earth's surface, the news will tell you where the epicenter was. And the epicenter is the place on the Earth's surface, right above the focus. Energy travels out in waves from the focus. And those waves eventually reach where you are, and you feel the earthquake. This black line here represents the fault. The focus is where the movement occurs, and the body waves fall into two categories. P waves, P stands for primary, as in first, and S waves, S stands for secondary, as in second. The primary waves arrive first, and the S waves, which are slower, arrive second. The information about P waves will be covered in the assignment. The only thing I want you to remember from this lecture is that a P wave can pass through liquid material. It can pass through liquid water. It can pass through liquid rock in the form of magma. It can pass through any fluid. Here's an example of a P wave. It vibrates within this direction, not up and down. For example, if you pull on the end of a spring and release it, the energy compresses within the spring. The S wave is a lot bouncier. It will not pass through any liquid. Liquid rock, for example, which a lot of the outer core is made of liquid rock. It moves up and down. Here, this illustration shows how an S wave moves, up and down. The S wave, to a human being, is often the part that's felt. The P wave might get your attention. Maybe you've had the experience during an earthquake where everybody stops what they're doing and makes eye contact, and then the shaking happens. Well, that moment when you stopped and paused and braced yourself, you were feeling the P wave, and then hopefully you were under a table or someplace safe before that bouncy S wave starts hitting where you are. Of course, damage is worse in the epicenter, right above the focus. The further you are from the epicenter, the less damage usually occurs. We measure an earthquake in three ways. Let me go back there. Seismometers, seismograms, seismographs. You don't need to worry about all these terms. I really just want to show you what a seismometer looks like. It's a box with a weight, with a pen, and a rotating drum of paper, like a big spool of paper. And if the earth moves, this weight goes back and forth, making marks on the paper. By the way, we do this with computers now, but classic seismometers were invented well before computers were invented. As you can see, this is not extremely high tech, even if it is clever. These were invented, by the way, in Pasadena, California. So, what does this measurement look like? Here's an example of a seismogram. First, the P wave hits, then the S wave hits, and then a whole bunch of other crazy waves hit. If you go on in geology, you will learn about these other crazy waves, the surface waves, and what kind of damage they do. In Geology 1, you're only responsible for P waves and S waves. What's neat about P waves and S waves here on a piece of paper is they can tell you how far away you were from the earthquake. You might notice that every line here represents 1 minute, so keep that in mind. We're going to use that seismograph to find the distance from wherever you are to the earthquake. Let's say, here, let me go back. Between the P wave and the S wave, about 5 minutes passed. Well, if I go up to this chart and find 5 minutes, it tells me, oh, I was 3,500 kilometers from the epicenter. Now, to actually find the epicenter, we need 3 people to feel the earthquake and look at a seismograph. If we have information from 3 different places, we can always find the epicenter and the focus. For example, Sao Paulo, Brazil, Montreal, Canada, and Paris, France all measure an earthquake. Using the seismograph, they determine how far they were from it, and each draws a circle around their city, the radius of that circle being the distance they calculated. Now, someone in Paris doesn't know where on the orange circle the earthquake happened, they just know where the circle is. So, if 3 people, or 3 locations rather, make a circle, the 3 circles will intercept right at the epicenter. Because 3 places are required, just like 3 sides in a triangle, this method is called triangulation. Well, we know where the earthquake is, but how do we talk about how strong it was? There are 2 ways, intensity and magnitude, to talk about strength. Intensity is not a measure you hear about on TV. So intensity really measures the damage, rather. So this is used with the modified Mercalli scale. This is different than the Richter scale. And like I said, it's used by scientists and not so much by the general public. The modified Mercalli scale really describes what the earthquake was like. Did it knock down buildings? Were there cracks in the ground? Did it wake up sleeping people? Was it totally gentle? These are very qualitative descriptors. Now, compare that with the Richter scale, which you've seen or at least heard of. Now, in the Richter scale, we have these different numbers, and in the Mercalli scale, we use Roman numerals. The Richter scale will measure magnitude, and if the earthquake is huge, we use something called moment magnitude, which is starting to pop up in the news in sort of following some recent very large earthquakes in Japan from just a few years ago. Now, this talks about the Richter scale being logarithmic. What does that mean? What that means is a 3.5 is 10 times stronger than a 2.5, 10 times more energy released. A 4.5, once again, releases 10 times as much energy as a 3.5 and 100 times more energy from a 2.5. The point of this is the difference between a 6 and a 7 on the Richter scale is immense. You would need 10 6.0s to be as strong as one 7.0. Where do earthquakes happen? Well, they happen at plate boundaries, and you know this from plate tectonics. You also know there are 3 main types of plate boundaries: divergent, convergent, and transform. A divergent boundary, of course, will have normal faulting associated with it. All of these little faults in the divergent zone will have earthquakes. The rift in East Africa, very famous divergent boundary, has many earthquakes. A convergent boundary, as you already know, is probably the most destructive because these have subduction zones, and these occur where plates collide. For example, here in the US of A, at the Cascades up in Washington, here's Mount Rainier, for example, we have two plates colliding and they cause enormous earthquakes, as well as create volcanoes. Most earthquakes on planet Earth happen in one of two places: the circum-Pacific belt, so around the Pacific Ocean, and the Mediterranean to Himalayan belt. The circum-Pacific belt is this. You may know it as the Ring of Fire. And the Himalayan, actually right here, this connects with this. The Mediterranean and Himalayan belt is probably number 2. It doesn't even compare, though, to the amount of earthquakes here, although it does have giant earthquakes. 100% of the deep focus earthquakes on this planet happen in the circum-Pacific belt. Now, if you ignore the West Coast in the US, the West Coast by far and away has the most earthquakes. There are some other places that have earthquakes, like the Rocky Mountains. So you can have an earthquake in Colorado. And believe it or not, east of the Rockies, none of these are quite as strong as the ones we have out west, but they can happen. Now we're going to talk a little bit about the damage. This is actually the most important part of this subject because, as you know, there's no such thing as a natural disaster without people. The disaster is really a measure of suffering or inconvenience that happens to humans. And that damage can take the form of toppled buildings, fires, gas main breakages, landslides, liquefaction, permanent land displacement, tsunami, foreshocks, and aftershocks. We're going to end this portion with this picture of San Francisco from the early 1900s. This is the Great Fire caused by the earthquake, and the fire, of course, did a tremendous amount of damage.